Hello to you Tenfolders. Welcome to another awesome edition of Tenfold Live. My name is Sibisiso and I'm coming to you live, guys, to bring you an exciting revision session of mathematics on a beautiful Monday afternoon where we're going to be covering the revision of grade 12 mathematics. Remember, this show that is specifically for you is proudly brought to you by Liberty. A very big shout out goes out to Liberty for giving us the opportunity to share all these awesome ideas that we're going to be sharing with you on this jam-packed program where we're going to be helping you with the revision of mathematics, taking questions from you across all the mathematics topics, anything and everything that you could be working on wherever you might be in your own corner. If you need assistance with that, we are here for you. We take questions via our app. If you want to know where this app is found, just go to your app store, search for what we call the Tenfold Education app. You'll find it. It's got awesome content on it. It will help you with the basics from grade 10, 11, and 12 of mathematics as well as physical sciences. In addition, there's life sciences. We're still working on uploading those ones. Remember, this app also allows you to send questions to us. If you go on the options, you click the drop-down menu, you'll find one of the options is called the tutor option. On that, you can then, of course, click there. There's a fellow waiting for you to send a question in a form of a picture or a video. You can even type it out. It depends on how you prefer to send that question to us. Besides that, on this app, there are videos because we understand that you guys need lessons. Maybe you missed lessons somewhere. You've got gaps of the content covered somewhere else, and you need anyone to help you with maybe covering some of the basics. We've got awesome videos on that particular app. I promise you, you will never regret. If you haven't downloaded the app yet, please go to your app store and make sure that you get yourself that particular app. But today, on today's show, we're going to be focusing on revision. We want to revise. So if you still have questions, please send them through to us and show some love on our Mindset Facebook page on www.facebook.com/mindsettv. Just say hi there and then inform all the others that are not watching that they're missing on the opportunity to multiply the content coverage tenfold and beyond. Without any waste of time, like I said on today's program, we're doing revision. I'm very excited. It's going to be a very jam-packed show with a lot of very exciting questions, all of them there to try and help you to understand. So now, let's start with the questions that we want to assist you with. The first one is an interesting question that comes from differential calculus. Let's go right into it and see what is going on here. Right. So this is, if you look at it, right, it's question 6 and it has the following. It has the following information. It says the graph of y equals to g prime of x is equal to ax squared plus bx plus c, and h of x equals to x minus 4 are sketched below. The graph of y equals to g prime of x equals ax squared plus bx plus c is the derivative graph of a cubic function. Very interesting, right? You're looking at it, it looks like a quadratic function. It is a quadratic function, but just remember that this quadratic function is derived. It's the derivative that you get from a cubic. Very important. The graph of h and g prime have a common y-intercept at point E, c with coordinates -2:0, and d with coordinates 6:0 are the x-intercept of the graph of g prime. A is the x-intercept of h and b is the turning point of g prime, and AB happens to be parallel to the y-axis. So very important. That just tells you that whatever the x-coordinate at A is, you'll get the same x-coordinate also at point B, because that line there happens to be is parallel to the y-axis. Very interesting pieces of information. You're likely going to need these in trying to answer questions, right? So it's very important for you to always read the love letter so that you understand what you are dealing with, because there's key information that appears on the story that you might miss. So please always make sure that you analyze the love letter fully before you begin looking at the questions. The first question that we see here says to us, if you look at it right there at the bottom, it says we must write down the coordinates of point E, right? Write down, right? Now, normally when people say write down something, it means it's easy to find it. In fact, you don't even have to do any fancy calculations. You just look at the diagram or you look at the information that was given to you, you should see your answer from there. So what is the way I'm going to look at this? E is the y-intercept of what? Of both the graph, the straight line and the parabola. Now, the straight line happens to have good enough information. We have the entire equation of the graph of h of x. So in order for me to answer that first question, I'm going to say the answer for E. So here's the number 1. Point E, the coordinates of E are going to be 0, and the y-intercept of the straight line. Remember, the equation of h was given to us as 2x minus 4. So you should know by now that this number gives you the coordinate, the y-coordinate of the y-intercept. So that means the coordinates of E will be 0 and negative 4. Right. Moving on to the second part of the question. The second part of the question says we need to determine the equation of the graph of the inverse. Right. We want to find the equation of the parabola, the graph of the derivative, the g prime. Please don't confuse the inverse with the derivative. We're dealing with the derivative here. Right. So we want to find that equation, the equation of that derivative. So what do we know so far on the parabolic function? We know its x-intercept. We know it's passing at point C, and we also know it's passing at point E, D, and we also know the coordinates of point E. We just found them from the previous calculation. Right. So if you allow me, let's just put it here and say for number 2, we are interested in the equation of the quadratic function. Right? That quadratic function has the following x-intercept. It's passing at negative 2 here. It's passing at 6 here. And it's passing through some random point E with coordinates 0 and negative 4. So how do you find the equation of a quadratic function or a parabola? You always begin by saying y is a into x minus x1 into x minus x2. Some people put x1 and x2 as r1 and r2, which is a bit more descriptive, right? Some people write r1 here and they put r2 here because those r's denote the roots of the graph, and the roots are basically where the graph cuts the x-axis. So it doesn't matter how you want to do it. So now I'm going to begin by firstly substituting my x1 and my x2. My x1 is the x-intercept at negative 2, and my x2 is the x-intercept at 0.6. So I'll have x minus, so it's minus 2, so that's going to give us plus 2, very important. And then we're going to have x minus, the other value there is 6, which I'm going to write there. So those points, the green numbers, they come from the x-intercepts. Now, once you're done doing this, once you're done writing down the x-intercepts as your roots, you then look for any random point where this graph is passing, and then use those coordinates as just simply x and y. So where I see y, I'm going to write negative 4, very important, equals to a into, right? And where I see x, right? Remember, we still have a plus 2 here, and we've got a minus 6. So that x of 0 is working twice. Be careful of that. Wherever I see x, I'm just replacing with the number 0, right? Okay, then from here, it's just basic algebra, trying to simplify. You've got negative 4 on the left. 2 times negative 6 is basically negative 12. So you're sitting with negative 12 times a. You divide both sides by negative 12. Your a ends up as being 1 over 3 because 4 over 12 is just 1 over 3, right? Now, once I'm done with this, I now need to take it back to the standard form of the equation. So I'm basically going to say, okay, remember we know it's a into those brackets, but we now know our a value is a third of x plus 2 and then x minus 6. Then it's just a matter of cleaning this up. Let's just see what will happen. This is going to be a third. So those brackets, when you're doing what you people call FOIL, you'll end up with x squared minus 4x minus 12, right? Then you come with that 1 over 3, so 1 over 3x squared minus 4 over 3x. A third of 12 is just going to give you 4. So this is basically what I'm ending up with as the graph of G. How did the examiner ask us to represent this? Well, they just said to you, if you check the question clearly, let's go down and find it. It says, find the equation of the graph G prime in the form y equals 2. So we just did that. We can just be nice to indicate that we're finding the equation of G. Just put it this way. Just say G is y equals to a third of x squared minus 4 over 3x minus 4. Very awesome stuff, right? This is exactly what the equation of G would look like. The next question is asking for something even more interesting. They're asking you to write down the coordinates of the turning point of G. All right. Now, it is at this point where we need to talk about the relationship between a cubic graph and its derivative. You guys should know that if you've got a cubic graph and you try to draw its derivative, you're going to get a quadratic function. The relationship between the two is always with the x values of, first of all, the turning point. The x values of the turning points in the original become x-intercepts in the derivative. And obviously between the turning points, you've got the point of inflection. That will be the turning point of the derivative. What am I saying to you? Let's check it out. Right. So we are interested, remember, we are interested in writing the coordinates of the turning point of G, right? Let's go back and look at this question. Be careful of what they're asking you. The x coordinate of the turning point of G. Be careful. So G is the parabola. We are looking at that. We are interested in finding the x coordinate of this, right? There are about 4 ways I can find this question. And the most interesting one that I want to use now is to make you aware of the fact that this point, the x coordinate, is the midpoint of the x-intercept. It's exactly in the middle of the x-intercept. So if I want to find the solution to the 4th question, I can just simply say the x coordinate of the turning point is the sum, the average, in fact, of the x-intercept, because it is exactly between them, right? So it is basically -2 added with 6 divided by 2. That's actually going to be 4/2, which leaves you with exactly an answer of 2. That is the answer that you're looking for. Alternatively, somebody could have said, well, what if I was not aware of the fact that the turning point, the x value of the turning point, is in the middle of my x-intercept? Well, you can use a straight line. Remember, grade 12s, a straight line, we were given a straight line that passes at that point there, right? And we know the equation of the graph of h of x. We could have used that to try and find the x-intercept of that particular straight line of h, right? And remember, if you want to find the x-intercept, you're just going to make y to be 0. So you would have 0 is 2x minus 4, which would give you -2x is -4. And when you divide on both sides, you would get an answer of 4 divided by 2, which will give you exactly 2. So because of the fact that this is 2 at point where the green line cuts the x-axis, and we know B, which happens to be the turning point, is directly below that point, that would mean it also has the exactly similar x value. Very powerful, right? Absolutely exciting. Okay. So now we go into the second last question of these nice questions. They're saying to us now, write down the x coordinate of the point of inflection of the graph of G. Very, very important. The graph of G. I don't know if they wanted to say G or G prime. Now let's talk about it, right? The question says they want the point of inflection. They want the x of the point of inflection. I'm thinking wherever you got this question, they were interested in finding the turning point or the point of inflection of G prime, because a cubic has the point of inflection, but a quadratic does not have a point of inflection. It just has a turning point. So I think it's okay for us to edit the question and give you what we think was supposed to be the actual question, because a parabola does not have a point of inflection, but a cubic does have a point of inflection. So let's talk about that, right? Okay, cool. So now remember there's G and there's G prime, right? Oh, they're saying G and G prime. All right, so I'm the one who's actually confusing these things. Yeah, let's go back. Remember, guys, remember G. The graph of G prime is the one we are looking at here, right? So G is the graph which happens to be the cubic, the original. So the examiner was not asking about the derivative. They were basically asking about the original, the graph of G, the cubic. So they also want to find the turning point of the cubic. So we'll answer 6.3 and 6.4 collectively, right? Okay, let's go back and look at this. Very important. So what I did here, I just found the turning point of the parabola, but this is not the turning point of the cubic. In order for us to find the turning point of the cubic, we need to remember the following. So I'm continuing my question to say to you that if you've got a cubic graph, right, which looks however it may look, in this case, this one's going to look like the way we are currently drawing it. If you want to find the coordinates of the turning point, you need to compare that cubic, which in this case would be the graph of G, with its derivative. Now, its derivative will simply be a parabola that looks exactly like this, right? It's going to be a parabola that looks like this. So the similarities between this cubic graph and its derivative graph is the fact that the x-intercepts on the graph of G prime, right, on the derivative. So the derivative graph, the x-intercepts on the derivative graph are just simply the x-coordinates of the turning point in the original graph, which means since we know that we've got negative 2 and 6 as the x-intercept of the graph of G prime, it means the turning point of our cubic, the original, would be negative 2 and whatever the y value is, and the other one will be 6 and whatever the y value is. Now we found that the turning point of our parabola, the derivative graph, is exactly 2. We know that the value here is 2 at the turning point from this previous calculation here. That literally means then the point of inflection of this cubic graph will have an x value of 2 as well, right? So this is basically what it means. The relationship between a cubic graph and its derivative is that the coordinates of the turning point, the x, only x's, right? The x coordinates on the cubic graph of the turning point become x-intercepts in the derivative graph. And the point of inflection becomes the turning point of the derivative graph. So in order to answer those questions that we're asking, they said they want the x coordinates on the cubic graph. How would we actually express our answer? We'll then tell them the following. G of x is a cubic, right? Therefore, the x coordinates, okay, of its turning points, it has 2, not 1, of its turning points would be x equals negative 2 and x equals 6. So these are the x coordinates of its turning point. The next question was asking for the point of inflection, right? The x coordinate again. So the point of inflection is exactly in the middle, so that means it's going to be x equals to 2. So that will be the solution, which we just explained how to find. Great stuff right there. Okay. The last question for this is asking us to explain why G has a local maximum when x is negative 2, right? Why G has a local maximum when x is negative 2. Okay, cool. It has a local maximum when x is negative 2. So let's discuss that. What do we mean, first of all, when we say local maximum? Well, we're speaking about the fact that it's where it is happening to be stationary. Remember, I made a claim that if you are dealing with a cubic of the form g of x is ax cubed plus bx squared plus cx plus d, the derivative is going to be quadratic. So you're going to have 3ax squared plus 2bx plus c. Now, we were given this equation, right, in the drawing. We're given the drawing of the derivative, which happens to be quadratic. Now, I want to draw your attention to this value here, right? The parabola we're working with is a smiling parabola, which means it's a parabola that has a value of a which happens to be positive. So we can then obviously use the same argument to say if a is positive in the derivative graph, it was also positive on the original graph. That means a is also positive there, which means the cubic graph that has an a value that happens to be positive always looks like this. This is what it always looks like. Very important for us to keep this in mind. Now, this turning point, we just found it as one of the turning points, and the examiner is asking us to explain why is that going to be a maximum, a local maximum turning point when x is negative 2, right? Very, very important for you to keep that in mind. So we can use this argument of how the shape of the graph would look to justify the fact that negative 2 will definitely be the maximum turning point. However, the better way of explaining this is to use the derivative graph. Let's go back to the derivative graph and then focus on that number negative 2. So this number, which happens to be negative 2, is the one on the derivative graph that happens to be the x-intercept. Now, on this region, right, you're looking at the G prime graph, right? The derivative happens to be positive. Now, if the derivative or the gradient graph, right, is positive, it means what? It means our original graph is increasing, right? The fact that the derivative above the x-axis is positive implies that the gradient is positive, which means we can make a claim that this graph, before x was negative 2, the original graph was increasing, right? Before negative 2, the graph of G, the original graph, is increasing because its derivative happens to be positive. However, for this region here, after negative 2, you will see that the derivative suddenly starts becoming negative, right? So if the derivative is negative from -2 all the way up to 6, it means that the original graph is decreasing in that region, right? From that x value up to this x value, we can then see that the derivative is negative, which then implies that the original graph, g of x, is decreasing. Very important. Now, the reason why -2 would be a local maximum is because for all x values that are less than -2, the graph of g of x was increasing. Very important, right? And then for all x values after -2, the graph of g of x was decreasing. Okay? Therefore, that x value of -2 will definitely be the local maximum. Therefore, x equals -2 will be our local maximum turning point in this case, right? It's a maximum turning point for that particular region. The important thing that you need to keep in mind is when you're looking at a derivative graph, you're looking at the gradient graph, right? When the gradient is positive, the original is increasing. When the gradient is 0, the original is stationary, it's turning. When the gradient is negative, the original is decreasing. So before -2, it was increasing, it became stationary, and then it decreased. That's why -2 will be what we call an x value where the graph happens to be having a local maximum. Absolutely exciting question. Thank you very much for sending it through.